This is SpaceTime, Series 24, Episode 91. Coming up on SpaceTime, astronomers zero in on the source of the impactor that wiped out the dinosaurs, producing matter out of pure energy, and discovery of a galactic stream of galaxy clusters. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study claims the impactor, believed to have wiped out 75% of all life on Earth 66 million years ago, including all the non-avian dinosaurs, most likely came from the outer half of the main asteroid belt between Mars and Jupiter. The findings, reported in the journal Icarus, came as a surprise to scientists as it's a region of space previously not thought to produce many Earth impactors. However, computer modeling from the Southwest Research Institute in San Antonio, Texas, has shown that the processes that deliver large asteroids to Earth from that region occur at least 10 times more frequently than previously thought. They've also found that the composition of these bodies does match what scientists know about the dinosaur-killing impactor. Researchers combined computer models of asteroid evolution with observations of known asteroids to investigate the frequency of so-called Chicxulub events. Over 66 million years ago, a body estimated to be around 10 kilometers wide slammed into what is now Mexico's Yucatan Peninsula, forming a 150-kilometer wide crater, known these days as the Chicxulub crater. And it was this huge blast which triggered the mass extinction event that ended the reign of the dinosaurs. Over the last few decades, much has been learned about the Chicxulub event, but every advance has led to new questions. One of the study's authors, William Botke from the Southwest Research Institute, says two critical questions remain unanswered. Firstly, what was the source of the impactor? And secondly, how often do such impact events occur on Earth? To probe the Chicxulub impact, geologists had examined 66-million-year-old rock samples found on land and within drill cores. The results indicate the impactor was similar to a carbonaceous chondrite meteorite, and that's some of the most pristine material in the solar system. Now, curiously, while carbonaceous chondrites are common among the many kilometre-wide bodies that approach the Earth, none today are close enough in size to produce a Chicxulub impact with any reasonable degree of probability. To explain their absence, several research groups have simulated large asteroid and comet breakups in the inner solar system, looking for surges of impacts on Earth, with the largest ones producing a Chicxulub event. While many of these models did have interesting properties, none provided a satisfying match to what authors know about asteroids and comets. To solve this problem, Botke and colleagues used computer models to track how objects escape the main asteroid belt. They found that over eons, thermal forces allowed these objects to drift into dynamic escape hatches, places where the gravitational perturbation of planets could then push them into orbits nearing Earth. Using NASA's Pleiades supercomputer, the authors followed 130,000 model asteroids evolving in this slowly, steady manner for hundreds of millions of years. Special attention was given to asteroids located in the outer half of the main asteroid belt, the part of the belt furthest away from the Sun. To their surprise, they found that 10-kilometre-wide asteroids from this region strike the Earth at least 10 times more often than previously calculated. The result is intriguing, not only because the outer half of the asteroid belt's home to large numbers of carbonaceous chondrite impactors, but also because the author's simulations can for the first time reproduce the orbits of large asteroids on the verge of approaching Earth. In fact, the explanation for the source of the Chicxulub impactor fits in beautifully with what astronomers already know about how asteroids evolve. Overall, the authors found that 10-kilometre-wide asteroids, the sort that was involved in the Chicxulub impact, hit the Earth roughly once every 250 million years on average. And that's a timescale that yields reasonable odds that the Chicxulub crater occurred 66 million years ago. Moreover, nearly half of all impactors were from carbonaceous chondrites. Again, a good match with what's already known about the Chicxulub impactor. The new findings will help astronomers better understand the nature of the Chicxulub impact, while also telling scientists where other large impactors from Earth's deep past may have originated. So, What do we know about the story of the Chicxulub impact? Well, to use its correct term, it's the KT or Cretaceous Tertiary Boundary Event, although these days it's often referred to as the Cretaceous Paleogene Extinction Event. We know it occurred 66 million years ago when a 10 to 15 kilometre wide asteroid slammed into a shallow sea off the coast of what is now the Gulf of Mexico's Yucatan Peninsula. The massive impact released as much energy as 100 teratons of TNT. That's 1 billion times more energy than the Hiroshima and Nagasaki nuclear bombs used to end World War II. The collision triggered one of the largest mass extinction events in Earth's history, wiping out some 75% of all life on the planet, including all the non-avian dinosaurs. The initial impact, which created the Chicxulub crater, threw molten ejecta and debris high into the atmosphere. So high, some of it began orbiting the planet. Shockwaves from the collision circled the planet, triggering devastating earthquakes and, because it was over water, a massive tsunami hundreds of metres high. The earthquakes are especially interesting. They were so powerful they generated what scientists are terming land tsunamis, and they triggered volcanic eruptions which literally shook the entire planet, while burning debris from the impact ejecta began raining back down onto the surface. And that caused an intense pulse of infrared radiation which began cooking any life exposed to it, and combined with the molten lava flowing from the volcanic eruptions, it sparked global wildfires which devastated vast areas of the Earth, burning up vegetation and killing any animal life on the planet's surface that had survived the initial blast wave. Now all that's devastating enough, but it gets worse. The asteroid impacted the planet at a location rich in sulfur-containing gypsum, which was initially vaporized and dispersed as an aerosol into the atmosphere, only to fall back down onto the surface as highly caustic acid rain, burning anything it touched and causing long-term effects on the climate and food chain. Smoke and ash from the wildfires and volcanic eruptions, together with dust from the ejected debris, initially created a blanket-like greenhouse effect, preventing heat from escaping and causing surface temperatures to soar. Eventually, temperatures cooled, as the smoke, ash, dust and ejected debris blocked out sunlight for months if not years on end. This created what scientists are terming an impact winter, which caused temperatures across the planet to plummet. Evidence of the global nature of the impact event can be seen around the planet in the form of a dark boundary line in the geologic record. Known as the KT event boundary, it contains high levels of the metal iridium, which is rare in the Earth's crust but abundant in asteroids. While this massive impact destroyed an entire planetary ecosystem, it left the door open for a revolution in life, and of course that eventually led to Homo sapiens. This is SpaceTime. Still to come, producing matter out of pure energy, and discovery of a galactic stream of galaxy clusters. All that and more still to come on SpaceTime. Scientists have for the first time directly converted pure light energy into matter in a single process. The findings, reported in the journal Physical Review Letters, involved the creation of electrons and their antimatter counterparts, positrons, by colliding quantum packets of photons, in other words, light particles. This conversion of light into matter is the direct consequence of Albert Einstein's famous equation E = mc squared, which tells us that energy and matter are interchangeable. The historic experiment was undertaken at the US Department of Energy's Relativistic Heavy Ion Collider at the Brookhaven National Laboratory. The results were derived in detailed analysis of more than 6,000 pairs of electrons and positrons, produced in what's termed glancing particle collisions, involving gold ions being accelerated to within 99.995% the speed of light in two accelerator rings. An ion is essentially an atom stripped of its electrons. A gold ion, with 79 protons, carries a powerful positive charge. And accelerating a charged heavy ion to such high speeds generates a powerful magnetic field that spirals around the speeding particle as it travels, like a current flowing through a wire. If the speed is high enough, the strength of the circular magnetic field can be equal to the strength of the perpendicular electrical field. And that arrangement of perpendicular electric and magnetic fields of equal strength is exactly what a photon is, a quantized particle of light. So when the ions are moving close to the speed of light, there's a bunch of photons surrounding the gold nucleus, travelling with it like a cloud. Scientists with the relativistic heavy ion collider then push two of these clouds of photons moving in opposite directions with enough energy and intensity that when the two ions grazed past each other without colliding, the two clouds of photons interacted, producing electron-positron pairs in the process. In other words, producing matter. To show that these particles were indeed created out of pure light, rather than other processes such as quantum photons popping briefly into and out of existence, scientists analysed the angular distribution patterns of each electron relative to its partner positron. See, these patterns differ for pairs produced by real photon interactions versus those produced by virtual photons. One of the study's authors, Daniel Brandenburg from the Brookhaven lab, says the team also measured all the energy, mass distribution and quantum numbers of the systems, finding them to be consistent with theory calculations for what should happen with real photons. Other scientists have tried to create electron-positron pairs from collisions of light using powerful lasers, but Brandenburg says the individual photons within these intense beams don't have enough energy yet. One experiment at the Stanford Linear Accelerator Center in 1997 did succeed in producing matter out of energy using a nonlinear process. But scientists there first had to boost the energy of the photons in one laser beam by colliding it with a powerful electron beam. Collisions of the boosted photons with multiple photons simultaneously in an enormous electromagnetic field created by another laser produced matter and antimatter. But the Brookhaven results are different because they provide clear evidence of direct one-step creation of matter-antimatter pairs simply from collisions of light. This is SpaceTime. Still to come, discovery of a galactic stream of galaxy clusters, and solar orbiter and Bepi Colombo spacecraft about to make history with a double flyby of Venus. All that and more still to come on SpaceTime. Astronomers have discovered a never-before-seen galaxy cluster with a black hole at its centre, travelling at high speed along what can only be described as an intergalactic road of matter. The findings, reported in the journal Astronomy and Astrophysics, support existing theories that roads or threads of thin gas connect clusters of galaxies across the universe. These threads have been difficult to prove until recently because the matter they contain is so sparsely spread out it's eluded the gaze of even the most sensitive instruments. However, following last year's discovery of an intergalactic thread of gas at least 50 million light-years long, astronomers were able to observe a cluster of galaxies which were on this thread, clusters now being named the Northern Clump. The Northern Clump's moving along this thread or road at high speed towards two other much larger galaxy clusters, Abell 3391 and Abell 3395. By using data from the CSIRO's Australia Square Kilometre Array Pathfinder Radio Telescope and combining it with observations from the European Space Agency's XMM Newton and NASA's Chandra Space Telescopes, scientists were able to single out one large galaxy in the middle of the clump, complete with a supermassive black hole at its centre. The observations also suggest that the Northern Clump is losing matter as it travels. One of the study's authors, Antje Veronica from the University of Bonn, says the observations showed jets of matter streaming behind the galaxy like the braids of a running girl. However, there could also be smaller clumps of matter in the thread falling towards the Northern Clump. Professor Andrew Hopkins from Macquarie University is the leader of the EMU project, which contributed the Australian Square Kilometre Array Pathfinder data for the study. He says the shape and orientation of these jets provides important clues about the motion of the galaxy hosting the black hole. Overall, the observations confirm the theoretical view that the gas filament is an intergalactic road of matter transporting galaxies and even galaxy clusters towards larger nodes of superclusters. Hopkins says the observations show that matter travelling along these threads is falling into the clusters and will continue to enlarge them.
ASCAP has been taking observations for a while now as part of its early science and pilot stage set of observations in order to demonstrate the performance of the facility. The EMU survey was in a position to take a number of observations as part of these pilot observations. And one of the areas that we covered happened to include this pair of interacting clusters of galaxies. This quite a fascinating system. A galaxy cluster is a collection of galaxies that are all inhabiting the same region of space, bound together by their mutual gravitational pull. And we expect, over the history of the universe, that such large galaxy clusters formed as galaxies themselves fall together under the influence of gravity. And of course, galaxy clusters can also fall together under the influence of their own gravity, and this is what we're seeing here. In particular, this is a very rich system. It not only has the two main galaxy clusters falling together themselves, but other smaller structures nearby, smaller galaxy groups and smaller clusters. And this one particular feature, which is called the Northern Clump, has been identified as a particularly interesting area of study.
It appeared to be moving on a stream of matter towards these two big galaxy clusters.
That's exactly right. One of the advantages of modern astronomy is being able to put together data from many different facilities, many different telescopes. Here we're using data from a space telescope called eROSITA, which maps the universe at X-ray wavelengths and is very sensitive to the hot gas which fills the space between galaxies. And in particular, galaxy clusters are known to have a lot of this very hot gas, which is easily detectable at X-ray wavelengths. The eROSITA data has mapped this streamer of matter, as you say, linking the Northern Clump to the other galaxy clusters. And we're able to see how the Northern Clump appears to be moving through that, or as part of that streamer of material. And it does indeed seem to be falling into the other larger galaxy clusters, as we would expect, based on the simulations of the way normal and dark matter interact over the history of the universe. It's actually quite remarkable how similar this system is to some of the predictions made in recent simulations. And it really strongly reinforces our understanding of the way matter is clumped together to form stars and galaxy clusters over the history of the universe. One of the ways that we can get a handle on how this clump, this collection of galaxies is moving, is from the radio data from the EMU survey. One of the larger galaxies in the clump hosts a supermassive black hole at its core, and we believe that we know this because of the presence of the radio jets that we see emanating from the galaxy. Normally, these radio jets appear to come out in opposite directions from the poles of the black hole, kind of like the spillover of the material that the black hole is eating. And think about it as a cookie monster scattering crumbs everywhere, and the crumbs shoot out in opposite directions from the poles of the black hole. What we see in this particular galaxy is that the radio jets are not coming out in opposing directions at all, but they're angled. And this is to be expected if that material is being pushed back as the galaxy moves through hot, dense, gaseous intergalactic medium, such as the gas that we pick up with the X-ray data from eROSITA. So this is a very striking telltale of the way that the galaxy appears to be moving, and it's very much in line with our expectations. It's a very hot material, though, and it needs to be hot in order to generate the X-ray emission that we detect. And the jets themselves, definitely moving at close to the speed of light, are also quite tenuous in a sense. They're made up of extremely energetic electrons, and it's the electrons that produce the radio emission that we can detect with ASCAP in the EMU survey. But those electrons are very easily influenced by the hot matter that they're streaming through in the intergalactic medium. And it doesn't necessarily need to be incredibly dense, although it's definitely more dense than the intergalactic medium that we might find outside our own Milky Way galaxy, for example.
Well, that was going to be my next question. How does this compare with something like the Magellanic Stream or Magellanic Bridge, which links the large and small Magellanic Clouds with each other and with the Milky Way?
Well, it's definitely similar in a sense, but on a much, much grander scale than what we have in our own Milky Way neighbourhood. The Milky Way, of course, has the Magellanic Clouds and many other dwarf galaxy neighbours, but what we're seeing here are large elliptical galaxies that are perhaps 10 times as massive as the Milky Way itself that are streaming towards each other. So, in a sense, there are some similarities, but on a much, much grander scale, everything's scaled up in both mass and intensity.
But is it made out of the same sort of stuff? Is that the idea, that it's gas and dust and stars and that's providing a magic carpet ride, for want of a better term?
That's an excellent description. The main difference is that we're seeing the signature of the radio jets from the supermassive black hole. We don't have that feature in the Milky Way at all, and this is something which tends to be more common in large elliptical galaxies with a supermassive black hole that's being fed by a stream of gas internal to the galaxy itself. Obviously, there is the neutral hydrogen gas associated with these galaxies as well, although that's not part of the investigation that was just recently published. But that's the kind of material that we see in the Magellanic Stream and the Magellanic Bridge. That's gas that's being stripped from those dwarf galaxies as they fall into the Milky Way. And that process will definitely be happening in these other systems, the Northern Clump and the adjacent large galaxy clusters, because, of course, each of those systems will have its own entourage of smaller dwarf galaxies that will be progressively being gobbled up by the larger systems, although we're not seeing that explicitly here.
So the fact that the jets are being perturbed, does that mean that there's ionization and the fact that you're getting lots of X-rays caused by heat, that means this whole heavily ionized, I take it?
Yeah, very much so. And it's that ionized gas that is of particular interest in other respects as well, because one of the puzzles in astronomy, not only the question of dark matter and dark energy, which are kind of like the background puzzles that keep everyone busy, but the normal matter, the baryonic matter that makes up planets and people and everything else, is actually hard to track down. We believe that we can't account for something like 90% or maybe even more of the regular baryonic matter in the universe. And one of the most likely explanations is that it lives in this phase that we call the warm-hot intergalactic medium, or the WIM, a very whimsical name, but it's a particular state which is very hard to detect observationally because it's not hot enough to produce the X-rays that we see in this very hot gas in these clusters, but it's too hot to produce the kinds of emission that we might expect from being able to detect it with other kinds of telescopes, radio telescopes and optical telescopes. So it's another form of missing matter, and we think that the fact that the motions of the galaxies and the galaxy clusters in this system so accurately mimic the predictions from the simulations, that amount of missing baryonic matter must absolutely be present there, even though we aren't detecting it directly.
We're not seeing it in our own galaxy or our nearby galaxies either, are we?
That's exactly right. It's yet another one of the puzzles of the universe.
The overall picture is that this material is helping the Northern Clump move towards these other large galaxy clusters, Able 3391 and Able 3395, and it's smoothing the way for it, or are they all just moving in that direction because of the gravity there, because of the other two clusters?
So it's the mutual gravitational pull of all of the systems that are kind of drawing them all closer to each other. And over time, they'll all progressively settle into a gravitationally bound supercluster, if you like. And we do see such superclusters elsewhere in the universe that have been formed by these processes as well. And it tells us a lot about the way that galaxies are influenced over the course of their history and their evolution by living in such extreme environments. Our Milky Way itself doesn't live in that kind of extreme supercluster. We live in a little local galaxy group, but it's nowhere near as busy or as dense as one of these supercluster style systems. It'd be a little like comparing a small outback town to a massive urban centre like Sydney or New York. We're in our own little Milky Way neighbourhood, kind of living out in a small country town in comparison. And of course, galaxies evolve differently depending on the numbers of interactions that they have with their immediate neighbours that can trigger episodes of star formation. Those kinds of interactions can also drive gas towards the centre of the galaxy where the supermassive black hole resides, feeding that supermassive black hole and causing it to trigger these radio jets, which in turn can have an effect on future episodes of star formation in a galaxy. And so putting together that broader picture of galaxy evolution is one of the key drivers of making observations like this. Not just understanding extreme systems like this one in particular, but putting together the whole picture of how galaxies like our Milky Way and others even quite unlike our Milky Way have come into being and have changed over the history of the universe.
So Based on your observations, does this suggest more that we're part of the cosmic web or that we're more likely to be at the edge of a void?
Well, both, in fact. So we are in a local galaxy group, so we're not in a void so much. But of course, the groups are relatively low density environments compared to these extreme supercluster environments. So we're certainly closer to living in a void than galaxies in these types of superclusters would be. One of the goals with the EMU survey using the ASCAP telescope is in fact to map the largest number of such cluster systems known and to trace out the cosmic web in both the nearby universe but also at greater distances, higher redshifts, so that we get an understanding of the way that that cosmic structure itself changes over the history of the universe. We have a team of cosmologists as part of EMU who are looking in particular at the way those types of measurements can be used to understand properties of dark energy in more detail, for example. So EMU is a very exciting project. We're looking at quite a vast variety of different scientific areas, ranging from cosmology to galaxy evolution, and even looking in depth at our own Milky Way itself.
Knowing exactly where we are in the cosmic web would help us understand some of the properties of dark matter and dark energy.
Exactly right. One of the other projects that I've been involved with is measuring the distances to galaxies from their optical spectra to map the distribution of galaxies in the universe and to use that as a way of getting a handle on the properties of dark matter, because the shape of that galaxy distribution, how tightly or loosely galaxies clump together in these clusters, is one of the signatures of the way that dark matter operates. And different models for dark matter produce different predictions for how tightly or loosely bound those kinds of structures are. So a very exciting time and a very exciting opportunity to combine information from a variety of different surveys and different projects, as well as different telescopes.
Do we understand gravity?
We understand gravity pretty well. I think one way of thinking about that question is to ask Isaac Newton, do we understand gravity? And he would have said absolutely yes. Every observation that he could make or that he had access to, and indeed that scientists did for several hundred years afterwards, was entirely consistent with Newtonian gravity. It really wasn't until Einstein came along with the general relativity theory that we were in a position to identify the areas where Newtonian gravity breaks down and where you need to invoke general relativity to understand those tiny, tiny discrepancies. One of the challenges now is that general relativity works very, very well for pretty much all of the cases that we can imagine. And it's not clear whether we need a new theory of gravity. But of course, one of the discrepancies is the one that leads to the postulation of dark matter.
Yeah.
The need to invoke the existence of additional mass in order to retain general relativity's correctness on very, very, very large scales. We've got kinds of scales of galaxies themselves and of distances between galaxies. And this is where different theories of gravity start becoming potential alternative explanations as an alternative to dark matter.
This is the idea of gravity changing in strength at different distances.
That's exactly right. So regular gravity that we believe that we understand obeys a 1 over r squared law. In other words, if you double the distance between a pair of objects, the strength of the gravity between them will decrease by a factor of 4, and so on. But the problem is that as you measure, for example, the way that galaxies spin around their axes, you can calculate the amount of expected mass needed to produce that spin, and it differs from the amount of mass you can infer from the light coming from the stars within that galaxy. And so either there's more mass there that you can't see, hence dark matter, or there's a change in the way that gravity works on those very, very large scales. And there are a number of alternative theories that have been proposed. One of the most common is called MOND, which stands for Modified Newtonian Dynamics. There are many others now as well that use that same kind of principle and improve on it and refine it in various different ways. But I think the jury's still out as to whether we need a dark matter itself or we need to change our understanding of gravity to explain the way that galaxies move on those very large scales.
Is that really exciting?
Absolutely. I think it's impossible to get a sense of how significant Einstein's discovery of general relativity was. It absolutely changed the nature of physics in a very fundamental sense. If there is actually a need to change the way that we understand gravity again, that would be an equally momentous shift. But also understanding if dark matter is real and understanding what it is and how it operates in the sense of the physics of the dark matter, that would be equally momentous. I think really nailing down the question in either direction is the kind of Nobel Prize-worthy science.
Yeah, the standard model has so much to offer, but it doesn't offer everything.
It's one of the reasons that we continue to do astronomy. It's the excitement of discovery and knowing that for every question that you might resolve, two more pop up. There's always more to learn about the wonders of the universe.
That's Professor Andrew Hopkins from Macquarie University and leader of the EMU project. This is SpaceTime. Still to come, Solar Orbiter and Bepi Colombo making space history with a double flyby of Venus. And later in the Science Report, a new United States congressional report finds that COVID-19 did leak out of the Chinese government's Wuhan laboratory. All that and more still to come on SpaceTime. As we go to air tonight, the European Space Agency is making history, with two of its spacecraft undertaking almost simultaneous flybys of the planet Venus. The two spacecraft, Solar Orbiter and Bepi Colombo, need the gravitational swing-by to help them lose a little orbital energy in order to reach their destinations towards the centre of the solar system. The double flyby also offers an unprecedented opportunity to study Venus's environment from different locations at the same time. And just as importantly, from locations that are not typically visited by a dedicated planetary orbiter. The joint ESA-NASA Solar Orbiter mission is flying past Venus right about now, with its closest approach skimming just 7,995 kilometres above the planet. Throughout its mission, Solar Orbiter makes repeated gravity-assist flybys of Venus in order to get closer and closer to the Sun and to change its orbital inclination, boosting it out of the ecliptic plane, the imaginary plane around which the planets orbit the Sun, and into a higher angle to give it a better view, the first ever view in fact, of the Sun's poles. Meanwhile, the Bepi Colombo spacecraft, a partnership between ESA and JAXA, will fly by Venus in a few hours' time at an even lower altitude of just 550 kilometres. Bepi Colombo is on its way to the nearest rock to the Sun, the planet Mercury. It needs to undertake flybys of the Earth, Venus and Mercury itself in order to help it achieve Mercury orbit insertion against the immense gravitational pull of the Sun. Now, while the twin flybys are spectacular, there sadly won't be any high-resolution imagery of the event. Science cameras aboard Solar Orbiter need to remain facing the Sun, and the main camera aboard Bepi Colombo is shielded by the transfer module that's delivering the mission's two planetary orbiters to Mercury. However, two of Bepi Colombo's three monitoring cameras will be taking some photos around the time of close approach and also in the days after the planet fades from view. The cameras positioned on the Mercury transfer module will provide black and white snapshots and will also capture the spacecraft's solar arrays and antennas. During the closest approach, Venus will fill the entire field of view, but as the spacecraft changes its orientation, the planet will be seen passing behind the spacecraft's structural elements. Solar Orbiter has been acquiring data nearly continuously since its launch in 2020. Its 4 in situ instruments are measuring the environment around the spacecraft itself. Both Solar Orbiter, as well as Bepi Colombo's two primary spacecraft, the Mercury Planetary Orbiter and the Mercury Magnetospheric Orbiter, will be collecting data on the magnetic and plasma environment of Venus from different locations. Solar Orbiter and Bepi Colombo each have one more flyby this year. At the start of October, Bepi Colombo will see its destination for the first time, making the first of 6 flybys of Mercury, with this one from just 200 kilometres above its surface. The two planetary orbiters will achieve Mercury insertion in late 2025, tasked with studying all aspects of this heat-soaked world, from its core right up to its surface processes, its magnetic field and its exosphere, in order to better understand the origin and evolution of the planet close to its host star. Meanwhile, in late November, Solar Orbiter will make a final flyby of the Earth, flying some 460 kilometres above the planet's surface, kicking off the start of its main mission. Solar Orbiter will continue making regular flybys of Venus designed to progressively increase its orbital inclination in order to ultimately allow it to observe the Sun's uncharted polar regions, which are key to understanding the Sun's 11-year solar cycle and the space weather it generates, which can have such a devastating effect here on Earth. This is SpaceTime. And time now to take another brief look at some of the other stories making news in science this week with a science report. A United States congressional report has confirmed that Chinese scientists were manipulating lethal viruses under unsafe conditions at the Wuhan Institute of Virology prior to the coronavirus outbreak. The findings are fueling further suspicions that the deadly pandemic was caused by a lab leak. The report by minority staff at the House Foreign Affairs Committee found that the Wuhan lab was engaged in dangerous genetic modification research on coronaviruses at unsafe biosafety levels. Congressional investigators say Wuhan researchers sounded alarms on the safety of the lab in medical journals well before the virus emerged. The lab was undertaking performance gain-of-function research, a process by which viruses are made to be more powerful. The congressional report provides new information indicating the Chinese government sought to mislead the world about the experiments taking place there. Congressional investigators found that researchers at the lab had the ability to genetically modify coronaviruses as early as 2016 without leaving any trace of that modification. In fact, during that same year, 2016, French defense officials voiced concern that the Wuhan lab would be used by the Chinese government for military purposes. Now, none of this is new, but the congressional report goes further. It says there's mounting evidence that the COVID-19 coronavirus was accidentally released from the Wuhan lab prior to September the 12th, 2019, and possibly even as early as late August. The report says that when Beijing realized what had happened, Chinese Communist Party officials and scientists at the Wuhan lab began frantically covering up the leak, including taking their virus database offline in the middle of the night and requesting more than $1 million in additional security. The report says it's incumbent upon the United States and like-minded countries around the world to ensure accountability and implementation of the reforms necessary to prevent the Chinese Communist Party's malfeasance from giving rise to another pandemic during the 21st century. The new information is likely to increase pressure on the US government to sanction China and hold it accountable for the coronavirus outbreak. There are also calls for the Biden administration to demand a full-scale overhaul of the World Health Organization, which aided China in its cover-up. The World Health Organization says more than 8 million people have been killed by the COVID-19 coronavirus, with over 4.4 million confirmed fatalities and more than 205 million people infected since the deadly disease first spread out of Wuhan, China. Meanwhile, a new study warns that people need to keep wearing masks and social distancing even after they're vaccinated against COVID-19 in order to help combat new vaccine-resistant strains of the deadly disease. The findings, published in the journal Scientific Reports, claim new models of the virus's mutation rate show that vaccine-resistant strains are most likely to emerge once we reach 60% vaccination levels. The researchers modelled the likelihood of a vaccine-resistant strain emerging in a population of 10 million people. They found that if there's a relaxation in the use of masks and social distancing when most individuals in the population are vaccinated, the probability of the emergence of a resistant strain is greatly increased. They also found that a fast vaccination rollout decreases the probability that a resistant strain may emerge. The authors say measures such as mask wearing, extensive testing or social distancing should be kept throughout the whole vaccination campaign in order to allow any emergent resistant strains to naturally become extinct. A new study claims rising sea levels may mean fewer eruptions of volcanic islands. But the findings, reported in the journal Nature, also warn the threat of large eruptions remains. The authors reached their conclusions after analysing 360,000 years of eruption records from the Santorini volcano in Greece. They then compared that data with high-resolution sea level data, finding that low sea levels resulted in more eruptions. The mathematical modelling suggests that lower sea levels places less weight on top of magma chambers, thereby allowing magma to crack upwards through the crust, causing eruptions. A new study claims increased oxygen levels caused by the slowing of Earth's rotation could have paved the way for life on Earth to evolve. The findings, reported in the journal Nature Geoscience, theorise that increased day lengths in the early eras of the Earth as it gradually began to rotate more slowly allowed photosynthetic bacteria to release more oxygen, in turn allowing for the evolution of the planet's diverse range of animal species. The theory comes from observation of a sinkhole 80 feet below the surface of Lake Huron, where bacteria considered similar to the bacteria of the early Earth still thrive. Scientists found the longer the days, the more oxygen these bacteria release. A new study claims there's a link between average IQ scores and vaccination rates. Researchers found 5 out of the 10 American states with the lowest IQs are also among the 10 states with the lowest rates of fully vaccinated adults, and half of the 10 smartest states rank among the 10 most vaccinated ones. But Tim Mendham from Australian Skeptics says while he believes that getting vaccinated is better than not getting vaccinated, he has concerns about the research and its methods.
You're talking about American states and average IQ levels in American states. And to me, there's always issues with measuring IQ anyway, right? And then
IQs are
getting
as
average.
good as the IQ test that is.
That's exactly right. Yeah, well, yeah, like most tests, etc. Yeah, and there was a lot of judgment put on top of these things. And getting an average IQ doesn't mean a lot. But they're suggesting that the states in America with the lowest average IQ, and don't forget, the difference between the lowest and the highest is about 10 points, right? You're not talking genius level versus, I forget what the actual terms are, idiot level or whatever. The interesting thing is that for the states that have a higher IQ, they tend to be, it's not absolute, but they tend to be in the highest vaccination rates. And that the states with the lowest IQ, average IQ, as dubious as that measure might be, have lower vaccination rates. Not all of them. It's not like the top 10 IQ has the top 10 vaccination rates. It doesn't work out that way. But there's none of the ones in the top 10 IQ who are sitting in the lowest vaccination rates, for instance. Interestingly, virtually all the states that are listed as the top 10 intelligence are in the east coast of the US or near the east coast, certainly the eastern side of the US, except for one, which is Hawaii. And California doesn't rate in the top 10 as far as I recall.
Well, that's no surprise.
To me, it's you could say that people with I don't even like using the term IQ. I think it's a really, it's a weird thing. Lower education, and they're also saying that, of course, that education is not necessarily an indication of IQ, as we know that people with a higher education are not necessarily immune to all sorts of strange ideas. But the suggestion is that people with a lower scientific literacy, like they don't understand science as well as others, might be anti-vaccine. They might be more prone to conspiracy theories and misinformation and that sort of stuff. It's not an absolute thing. It's not sort of that clear cut. But I mean, and if you equate low scientific literacy, you say that's caused by low IQ. Well, if you want to go down that track, you can go down that track. It's so many issues with that sort of study and the variables. It's interesting. Is it reliable?
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.